Synchronous motor. A synchronous electric motor is an AC electric motor in which, at steady state, the rotation of the shaft is synchronized with the frequency of the supply current. The rotation period is exactly equal to an integral number of AC cycles. Synchronous motors contain multiphase AC electromagnets on the stator of the motor that create a magnetic field which rotates in time with the oscillations of the line current. The rotor with permanent magnets or electromagnets turns in step with the stator field at the same rate and, as a result, provides the second synchronized rotating magnet field of any AC motor. A synchronous motor is termed doubly fed if it is supplied with independently excited multiphase AC electromagnets on both the rotor and stator. The synchronous motor and the induction motor are the most widely used types of AC motors. The difference between the two types is that the synchronous motor rotates at a rate locked to the line frequency since it does not rely on current induction to produce the rotor's magnetic field. By contrast, the induction motor requires slip. The rotor must rotate slightly slower than the AC alternations in order to induce current in the rotor winding. Small synchronous motors are used in timing applications such as in synchronous clocks, timers and appliances, tape recorders, and precision servomechanisms in which the motor must operate at a precise speed. Speed accuracy is that of the power line frequency, which is carefully controlled in large interconnected grid systems. Synchronous motors are available in self-excited sub-fractional horsepower sizes to high-power industrial sizes. In the fractional horsepower range, most synchronous motors are used where precise constant speed is required. These machines are commonly used in analog electric clocks, timers, and other devices where correct time is required. In higher power industrial sizes, the synchronous motor provides two important functions. First, it is a highly efficient means of converting AC energy to work. Second, it can operate at leading or unity power factor and thereby provide power factor correction. A synchronous motor is generally made up of two parts: a stator, the stationary part of the machine that carries the armature winding in which the voltage is generated, and a rotor, the rotating part of the machine that produces the main field flux. The stationary part of the machine is called stator. It includes various parts like stator frame, stator core, stator windings, and cooling arrangement. The stationary part of the machine is called stator. It includes various parts like stator frame, stator core, stator windings, and cooling arrangement. They are explained below in detail. Stator frame. It is the outer body of the machine made of cast iron, and it protects the inner parts of the machine. Stator core. The stator core is made of silicon steel material. It is made from many stamps which are insulated from each other. Its function is to provide an easy path for the magnetic lines of force and accommodate the stator winding. Stator winding. Slots are cut on the inner periphery of the stator core in which three-phase or one-phase winding is placed. Enameled copper is used as a winding material. The winding is star-connected. The winding of each phase is distributed over several slots. When the current flows in a distributed winding, it produces an essentially sinusoidal space distribution of EMF. Rotor made of silicon steel lamination. The rotor has slots which accommodate solid conductor, and ends of rotor conductor is short-circuited by means of end rings. Rotor core is mounted on rotor shaft to which bearings and caps cooling fans are mounted. Field winding. It is wound on the former and then placed around the pole core. DC supply is given to it through slip rings. When direct current flow through the field winding, it produces the required magnetic field. Damper winding. At the outermost periphery, holes are provided in which copper bars are inserted and short-circuited at both sides by rings forming damper winding. Rings. Slip rings provide DC supply to the rotor windings. Brushes. Brushes are made of carbon, and they slip over the slip rings. A DC supply is given to the brushes. Current flows from the brushes to the slip rings and then to the exciting windings. Bearings. Bearings are provided between the shaft and the outer stationary body to reduce friction. They are made of high carbon steel. Shaft. The shaft is made of mild steel. Mechanical power is taken or given to the machine through the shaft. The principle of operation of a synchronous motor can be understood by considering the stator windings to be connected to a three-phase alternating current supply. The effect of the stator current is to establish a magnetic field rotating at 120 p revolutions per minute for a frequency of f Hz and for p poles. A direct current in a p pole field winding on the rotor will also produce a magnetic field rotating at rotor speed. If the rotor speed is made equal to that of the stator field and there is no load torque, these two magnetic fields will tend to align with each other. As mechanical load is applied, the rotor slips back a number of degrees with respect to the rotating field of the stator, developing torque and continuing to be drawn around by this rotating field. The angle between the fields increases as load torque is increased. The maximum available torque is achieved when the angle by which the rotor field lags the stator field is 90°. Application of more load torque will stall the motor. This additional rotor winding is usually referred to as a damper winding because of its additional property of damping out any oscillation that might be caused by sudden changes in the load on the rotor when in synchronism. Adjustment to load changes involves changes in the angle by which the rotor field lags the stator field and thus involve short-term changes in instantaneous speed. These cause currents to be induced in the damper windings, producing a torque that acts to oppose the speed change. Types of synchronous motor. Depending upon the method of magnetization of the rotor, there are two types of synchronous motors: non-excited, direct current excited, non-excited motor. In these motors, the rotor is magnetized by the external stator field. The rotor contains a constant magnetic field. High retentive steel such as cobalt steel is used to make the rotor. These are classified as a permanent magnet, reluctance, and hysteresis motors. In permanent magnet synchronous motors, a permanent magnet is used along with steel for rotor design. They have a constant magnetic field in the rotor, so induction winding cannot be used for starting. Being used as gearless elevator motors. In reluctance motor, the rotor is made up of steel casting with projecting tooted poles. To minimize the torque ripples, rotor poles are less than stator poles. Contains squirrel cage winding to provide starting torque to the rotor. Used in instrumentation applications. Hysteresis motors are self-starting motors. Here the rotor is a smooth cylinder made up of high coercivity magnetically hard cobalt steel. These motors are expensive and are used where precise constant speed is required. Generally used as servomotors. DC current excited motor. Here the rotor is excited using the DC current supplied directly through slip rings. AC induction and rectifiers are also used. These are usually of large sizes such as larger than 1 horsepower, etc. When a three-phase supply is given to the stator winding, it sets up a rotating magnetic field in space. This rotating magnetic field has a speed which is known as the synchronous speed. This rotating magnetic field induces the voltage in rotor bars and hence short-circuit currents start flowing in the rotor bars. These rotor currents generate their self-magnetic field which will interact with the field of the stator. Now the rotor field will try to oppose its cause, and hence rotor starts following the rotating magnetic field. A wound rotor induction motor is defined as a special type of three-phase AC induction motor designed to provide high starting torque by connecting an external resistance to the rotor circuit. The motor's rotor is a type of wound rotor, hence why it is also known as a wound rotor or phase wound induction motor.